when you had this idea of organizing the retreat. So yes, I'm delighted to be here, and I'm delighted to see you. I want to say that we do many things and they involve a lot of work, right? But this is, I find it really, really rewarding. So thank you. Okay, so I will talk about my research work that I did in the past few years. And this is on liquid crystal elastomers. First of all, because it's an interdisciplinary audience, I will try and introduce things in a gentle way, so to give you a flavor of what this work is about. So liquid crystal elastomers are practically rubber combined with liquid crystal, the liquid crystal that you know from smart displays. As a material, it was envisioned by Pierre Dejean, who is the Nobel Prize laureate for liquid crystals, but that was in the 1975, but it was only synthesized a few years later and successfully, and in order to be able to repeat this synthesis. And the theoretical foundation came much, much later from Mark Warner and Eugene Terentchev, both at Cavendish Laboratory in Cambridge. What is shown here in these pictures are molecular dynamic simulations that we carried out a few years ago. So just to show the structure, how the polymeric chains are cross-linked with liquid crystal mesogens. Here you see the phase transition under change of temperature. So this is a thermotropic liquid crystal. Liquid crystal can also be made phototropic if some special dye molecules are cross-linked together with the liquid crystal and the polymeric network. And in that case, the response is under light. I will mention that a bit later. But the most common ones are the thermotropic liquid crystal elastomers. So on the left, you see the isotropic state where the liquid crystal mesogen are randomly oriented. This is at high temperature, and then if you cool it enough, you get a nematic state where there is the mesogens tend to align, and I hope you can see the end there. That will indicate the mean direction, the average direction of these molecules, giving you the so-called director. So this is an important concept in the theory of liquid crystal and liquid crystal elastomers. Because it's rubber combined with liquid crystals, there are a number of physical properties that liquid crystal elastomer inherit from the rubber material and enhance as well. So one of these effects is the Gauge-Joule effect, and this is what makes thermotropic liquid crystal elastomer very, very effective. In the Gauge-Joule effect, for rubbers, for pure rubber, is the tendency of stretch elastomers to contract when heated. So that is very hard to observe in rubber, but it's still observable. It was observed by Go, studied later by Joule, but in liquid crystal elastomers, because of the presence of the liquid crystal mesogens, this can be observed with naked eye. As you can see, it's quite a large difference in centimeters. So if you start with the liquid crystal elastomer, where the nematic director is in the vertical direction, so the mesogens are aligned vertically, then you have this length of the sample, and then when heated, you can see that it shortens visibly. That's because the mesogens become disordered, so that nice order is lost. But again, when cooled, it's retrieved. So the material remembers the order. And this is reversible and repeatable. So it's a very elastic phenomenon. Well, there is no pure elastic material, not even rubber is purely elastic, but it's quite realistic to model it as elastic. There are also phenomena that are not present in pure rubber, and one such phenomenon, which is now a signature for liquid crystal elastomer is this so-called shear striping. So I'll explain what happened here. You start to the sample stay at the top there. You see that it's transparent. This transparency indicates that the mesogens are well aligned. But the alignment in the original sample is designed to be in the vertical direction. So for that sample, you have aligned mesogens that they're aligned vertically. Then the sample is extended perpendicular to the director. And you see that the sample becomes opaque. So what happens there, it appears to be a loss of alignment at some stage. And then if you continue stretching the material, again, it becomes transparent, indicating that there is again alignment. So what happens, in fact, is that in between stage, there is still alignment, but this alignment is alternating in some form that it forms this so-called, we call them shear striping, because some mesogens, so on one stripe, the mesogens rotate to the left. On the next stripe, they rotate to the right, and so on. So basically, what the mesogens do, because they're free to rotate, they will rotate in order to become aligned with the force. If the force is large enough, they will want to follow the force, but there is so basically it's about the energy. So they find a minimum way of aligning with the least energy, not by all of them aligning together, but alternating, and depends on the composition, the number of stripes will differ. Here is a successful finite element simulation by my PhD student, and I must say that it took him a while to get it. So it's not so easy to get these simulations done, but yeah, they do occur. Okay, so how about the mathematical modeling? How do we model that? I mentioned this, the rubber part of the material is important. So obviously it's kind of natural to build the liquid crystal elastomer theory on the existing rubber theory, and combining, of course, with the liquid crystal theory. So we will be using a phenomenological model. Okay, so this means that it captures the macroscopic behavior of the material, and we define this strain energy function in terms of F. This will be the deformation gradient, and Q, which is going to be the order parameter tensor for liquid crystals. And we decouple them. Okay, it doesn't have to be like that. They can also be coupled. We decouple them into the elastic part and the liquid crystal part. And the elastic part is practically the elastic strain energy density that one can also find in rubber theory, with F being the macroscopic deformation tensor. Incompressibility is generally accepted as a good assumptions, simply because rubber is also modeled as incompressible. So incompressibility means that the volume of the material does not change when whatever deformation you apply to the material. It's practically that it remains pretty much the same. Okay, I already defined the pneumatic director, so N will be a pneumatic director. Now, because deformations are large and because the pneumatic director is free to rotate, there will be a pneumatic director. There can be a pneumatic director N0 that differs from the pneumatic director in the reference configuration, that differs from the pneumatic director in the deformed current configuration. The liquid crystal part is typically taken as for thermotropic, is taken as the Landau-Dögen expansion of the pneumatic free energy with A, B, and C material constants, A depending on temperature. And a bit more about the macroscopic deformation tensor. So the macroscopic deformation tensor contains information from the nematic order in the reference configuration through G0, the elastic deformation through A, and nematic deformation in the current configuration from G. And so you can see that in G and G0 there is a coefficient C and C0 that is length scale length scale parameter. And for example, this can be derived if you assume compressibility. So in the case of compressibility, that will be easy to derive. And you can see here a schematic of this decomposition. So if you start with the reference configurations being the cross-linking state. So what's this cross-linking? When liquid crystal elastomers are produced, so there is usually a light, weak cross-linking to begin with, and then the material can be deformed. So a nematic order is imprinted on the material, and then another second cross-linking occurs. So G0 will be the cross-linking state, for the cross-linking state, and then there will be an isotropic state that for which the elastic deformation is defined, because rubber is isotropic. So A will be exactly what the rubber part of the material will be deformed by, and then G will be operating from the elastic deformation deformed state to the current configuration through the nematic response to temperature, for example, if it's thermotropic. Okay, the order parameter tensor. So we have a uniaxial order parameter, and it's possible to also have biaxiality, although this is rarer, but it can happen. So this is the notation for perfectly ordered nematic. Q is equal to A, but this is just a theoretical coefficient, but in general, in practice, Q is about 0.6. Q0 is for the isotropic state. B, if it's an uniaxial system, is going to be 0. If it's not a biaxial, if it's not a uniaxial system, is going to be different from 0. So these are just to take into account the ordering of the liquid crystal mesogens. So now we also have some requirements for the strain energy densities, and again these are inherited from the rubber theory. And one of the first one is objectivity, so meaning that this constitutive model is unaffected by superimposed rigid body transformation, and because N is defined with respect to the deformed configuration, it transforms when this configuration is rotated. So the rotation also applies to N. Isotropy means that the constitutive equation is unaffected by rigid body transformation prior to deformation. And in this case, the rotation does not apply to N because it's defined with respect to the deformed configuration. So this has to be clearly stated and has to be satisfied by the strain energy functions. And one very, very simple example is if we express the elastic part of the strain energy function in terms of the stretch ratios. So this would be the principle, the ratio between the deformed state and the reference state in the principal directions of the deformation. So we'll have lambda 1, lambda 2, lambda 3 for the macroscopic state, for the macroscopic deformation gradient F, and alpha 1, alpha 2, alpha 3 for the elastic part, for the purely elastic part. So this is the notation. We also care about this shear modulus. So in the linear elastic limit, the shear modulus is simply the sum of these coefficients, and this can be measured through macroscopic deformations, or it can be derived by statistical averaging. So this is a physical quantity that can be determined experimentally. Okay, so what happens if we use a model such as that one? I'm not specifying exactly the details of the model, but it's of that form. When we want to model the shear striping, so we can have an exact solution, and for you can see here the three stages. So the first stage in the blue curve indicates the energy when the nematic director is aligned vertically in the sample that I showed you. So the nematic director is happy to the minimum is attained with the director aligned vertically. At the end, when the sample has stretched enough, the minimum is attained for the nematic director being aligned in the force direction. However, you see that in the middle, neither of them wins. There is a third state. There is a third state which corresponds to the shear striping, and we can compute analytically the values of the shear parameter and the director angle, theta 0, for the stretch when the stretch in the main direction has values between these two bounds. And you can see that these bounds depend very much on the ratio between the purely elastic and the nematic part of the strain energy function. So I will not go into detail because it's I can have a whole talk on this. Okay, so the thing is, we have these deformations, and for some of them we can compute exact solution. For others, we need numerical methods. And the question is, what are those deformations for which we can, which we expect to be found in a class of materials, or rather material models? So what kind of material models, what class of material models we should aim for when trying to capture certain generic universal deformation? And we have a theorem which says that for an ideal unconstrained uniaxial nematic elastomer, by ideal meaning that we only take the strain energy to be equivalent to the elastic part of the strain energy. So we forget about the Landau-Deugen extension. So just the elastic part. In that case, if G0, if the gradient of the nematic deformation in the reference configuration is constant, and if the deformation gradient on macroscopic scale is piecewise differentiable of class C2 with a determinant positive. The determinant positive simply says that there is no interpenetration of the material. So this is again inherited from rubber. This deformation, so the only deformation that can be maintained in all class of these models are those for which both the deformation gradient F and the nematic component G are piecewise constant in Cartesian coordinates. So universal deformation in rubber, the theorem will just say that F is constant. So if it was just rubber theory, you wouldn't have the G or the G0, practically F will be equal to A. And in that case, the theory says that the only deformation that can be maintained by application of traction forces without any body forces only, so something that can be reproduced in the lab, are those for which the deformation gradient is constant, so the so-called homogeneous deformation. Here, we take into consideration piecewise constant deformations in order to capture that shear striping. In principle, you could have that in rubber as well, so there is no reason why you can't just say, okay, I can take it piecewise constant, or I can take it piecewise constant, I can take F to be differentiable of class C2, and this is fine. But that's not easily observed in rubber. So because it's not a phenomenon that's been reproduced in lab, it's not something that physically occurs. There is no need for such a theory. But in this case, because shear striping is also part of liquid crystal, it's a generic part of liquid crystal, it's been observed universally. it needs to be captured. However, when you have these two alternating steps, you need to have a coherent geometric compatibility, and in that case, the rank one connectivity is imposed. So the rank of F on one stripe minus of F for the neighboring stripe has to be equal to 1. So this is for geometric compatibility, so that the interface has a single normal direction, because otherwise you don't have that, and it doesn't make sense physically. So with this theorem, we actually state that for all models, that are defined like that, you will have this deformation should be captured. You should be able to capture them either analytically or computationally if it's too complicated and the function is too complicated. But basically, it's just using the so-called ideal nematic elastomers, which are only modeled by the elastic component. Okay, so how about applications? There are a range of applications that people can think about using these materials. And one such application that we've been involved with is for modeling braille displays. So refreshable braille display. These are very desirable because you do have the braille writing, right? You have you have it, for example, on pharmaceutical products, on boxes. You can feel it. You can see the size that is very small. But refreshable braille displays are also lend themselves to having computers or digital devices on which people can read the information, and these are actually very expensive to produce, and there are some products, commercial products, but they're very expensive and they're not very easy to find and not very easy to use. So there is a need for improving in that direction. I'm not saying that this is the solution yet, because talking to the physicists, they also say, well, between their experiments and finished product, it needs to be, the engineers actually need to be involved, and with different specialization. But it is a hope that this material can be used in this way. And you can see here on the right the actual sample in liquid crystal elastomeric sample, and these will be activated. So the braille dots will be activated by changes of temperature. With the liquid crystal elastomers, because liquid crystal elastomers can remember the nematic order for cross-linking at the correct temperature, then they can be generated by changing the temperature, probably with the electric field or something similar. Okay, so how did these experiments happen? So they had these molds. You can see they've got with these gaps, and then in between there's a layer of liquid crystal, and that will be compressed, and when deformed, the nematic molecules will be aligning in a specific way, and then it can be cross-linked, and then the material will remember that deformation. So we modeled this using actually a linearized model. There was no need for using a fully nonlinear model for this. So we used a linearized form of the strain energy function, and it was very interesting because, for example, when you deform a rubber and you compress it, there will be a bulging, right? So there will be a bulging in the gap. What also happened here is that when cooled, the material also had a gap underneath. So the so-called punt the word pant comes from, if you look at wine glasses, the wine glasses have that kind of traditional gap. Well, of course, nowadays, because the glass industry is so advanced, they can produce purely flat bottles, as you can see from beer bottles, but you only see those gaps in the wine bottle for traditional reasons. So people kind of keep up with the tradition by making an effort to produce that pant. But in the old days, when glass industry was something that people were doing on a smaller scale, the reason the manufacturer will be having that pant was because they wanted to make sure that the bottom is not concave. So they kind of twisted it up to make sure that it's not curved and doesn't sit on a flat surface. But yeah, that was inherited now. It's just they just do it for traditional reasons. They can make it flat if they want it perfectly. So it's very interesting that here we also observe this gap underneath, which is not observed in pure rubber. So the job here was to try and understand what happens to the nematic director, because it could not be observed experimentally. So there was the sample is too small, the layer is too thin to actually be able to visualize very clearly what happens. So with the model actually managed to capture the fact that the nematic director is aligning in the bulge, and then that alignment is actually remembered in the when the temperature changes. And for different temperature, you have different level of alignment, obviously. As you can see there, experimental. So that's experimental. This is computational. So the top is experimental, the bottom is computational. You can see different levels of bulging at different temperature. So that was and this is the sample. You can see the liquid crystal, and this is the colors indicate height, basically. So. Right, another application, which is also a theoretical model, really, is for a capacitor, for a charge pump electrical circuit, for capacitor in a charge pump electrical circuit. So what we have here is V1. It indicates a battery. It's an initial battery that has a voltage V1. So what we try to do, we try to raise the voltage V1 to V2 using a variable capacitor. So the diode just work at switches. The electrical circuit, the electricity can only flow in one direction. And with this one, the capacitor is filled, but also the battery can be recharged. So you can see that the voltage is raised to V2, but the battery can also be recharged through the circuit. And the arrow here indicates variables capacitor, and I'll explain what that means. So in this variable capacitor, capacitance changes. So C is capacitance, Q is charge, V is voltage. So we start with the nematic state. So the elastomer is in a nematic state at low temperature. And for this one, the capacitance is got Q1, which is the charge at under voltage V1. But then the elastomer is being heated. Say you want to harness solar heat. So if you can do it the same with light. So you change instead of heat, you can have light. So if it's heated or lit, if it is light that we want to harness, then the temperature increases, and the capacitance in that case decreases with, and I'll show the formula for capacitance to understand why it decreases. But because the charge is the same, the voltage will be increasing. And that can be done all the way up to the isotropic state. So the voltage will be V2, but then the charge also changes. And then when cooled, the reverse happen, and one can also charge the source battery. So this is what the capacitor looks like. So it's between two transparent electrodes, and we'll have a liquid crystal elastomer dielectric in between. The capacitance here you can see depends on the volume and on the permittivity, which is defined by epsilon. What else is in the notation? Yes. Okay, so you've got the surface area and you've got the distance. You can see that the capacitance decreases as the distance between electrodes increases. And if we have a liquid crystal elastomer that is initially in a nematic state, okay, then if it's heated, then it becomes isotropic. The sample will shorten, so the distance between electrodes increases, and the capacitance will be forced to decrease. So this is what happens. These capacitors are actually inspired also by those made of pure rubber, except that for pure rubber, it won't be the temperature or the light that will be harnessed, it will be mechanical energy. So all that deformation will be produced mechanically by some device, and that's been already used in smart shoes. So that just to harness the movement of the feet and other devices. But yeah, so smart clothing, smart shoes, the shoes are kind of on the list of desirable products using this kind of materials, just because you can harness that kind of mechanical energy for pure rubber. Here with liquid crystal elastomer, we can also harness heat or light because liquid crystal elastomers are highly responsive to this kind of stimuli. There are other, so this is for parallel electrodes. There are also some traditional types of designs with multi-layer structures. You can have several layers of these, and you can also have tubular section. Depends on the design, but the principle are pretty much the same. Okay, so in this case, we need to find the optimal work. So we take a strain energy function that is, so the first two terms are just from the ideal nematic elastomers based, and then the last term is captures the electric part of the energy contribution, and the net electrical energy, so it will be the output minus the input, and then we try to find the maximum generated output for this model. There are, however, some things that we need to be careful about, and namely that the material can wrinkle under certain deformation. Again, I won't go too much into detail, but that needs to be avoided. So wrinkling voltage needs to be avoided, and therefore you cannot have too high a voltage. So that's the conclusion here, that you need to have a voltage that is within some parameters that wrinkling is not triggered. But we can see here some kind of comparison. So for heat and light, pretty much the same, similar performance. What's compared here is the performance in the case when the material is not pre-stretched at all. So the liquid crystal elastomer is simply responding to the environmental changes like light or heat. Then we have the case when the material is pre-stretched perpendicular to the director and also pre-stretched parallel to the director. So perpendicular to the director is blue, parallel to the director is red, and without stretch is yellow. And you can see that stretching it parallel to the director actually makes it less optimal. And so there is no need to constrain the stretching in the parallel to the director, because the director, when changing temperature, will want to do its thing. We want to become disordered, and you want to harness all of that. If you restrict that, then you restrict the power of the capacitor, which makes sense physically. We just did it because it had to be just to cover all cases. The best case scenario is when you pre-stretch the material perpendicular to the director, and that's also inherited from rubber. So that's also observed in pure rubber. So you do it here. However, you remember that when you pre-stretch perpendicular to the director, you might have that kind of shear striping occurring. But because for this kind of dielectrics, the application of current between the electrodes will actually help the deformation, so that it is possible to avoid shear striping. So two things to bear in mind. You can just say, oh, liquid crystalline elastomers are great as dielectric, because they have this kind of instability. So you have to watch out for wrinkling, and you have to watch out for shear striping. So you kind of have to play the voltage in such a way that these instabilities are not triggered, because then the capacitor will be less efficient. But overall, for some model parameters, the performance is better. Mu1 and mu2 here are actually the ratio between the energy component that is just rubber. So if you model it just as rubber, and if you model it as an ideal elastomer, and you see that if mu1 is very, very large, so meaning that you practically model it as pure rubber, then there is no big advantage, except for the case if you pre-stretch it. So pre-stretching will still help, but otherwise there is no much response to the environment. However, if you model it more as an ideal elastomer, a pneumatic elastomer, so more along the ideal liquid crystal elastomer modeling, then the efficiency will be of the capacitor will be clearly visible. Okay, so one last thing to mention, because I keep mentioning light response as opposed to heat response of the elastomer. So for these ones, if the special dye molecules cross-linked in the material, then the elastomer can respond to light just in the same way as it responds to heat. And this is one paper where we had a reduced model for rod-like structures. So in this case, if light is shining from the left, there is a bending of this rod-like structure, just as it was observed in the experiments. But this model was not tuned to so it was not calibrated to the experiments. It's just a qualitative result, but it's a very, very rigorously mathematical paper. So you can do that for certain models, and very pleased. Right. So I think I'm going to conclude now, leave some time for discussion. So basically, the conclusion is that the theory of liquid crystal elastomers and the experimental work draw both expertise in elasticity and liquid crystal fields, and they're mutually dependent. Mechanical energy and stimuli response to stimuli are interdependent. So mechanical strength can give rise to changes in the crystalline order, and vice versa. Changes in the order, say due to environmental changes, will induce some mechanical stress and strains. And because of these very special properties, liquid crystal elastomer are top candidates for a range of applications that in mechanical engineering, power generation, etc. This is all I wanted to show you today. Thank you very much for your attention.
We have questions for Angela.